Okay, today I will explain one of the properties of the limits. Sometimes we have limits that we cannot apply the most common properties and rules to solve the limits, so that we have now the squeezing theorem. This is the definition of the squeezing theorem. If we have a function f of x in an interval where we can define another two functions, the function b of x and a of x, for all x that are close to the number that we believe is the limit, set possible that number, for example, that number, the limit doesn't have to be defined for the function f of x specifically. We say that if the limit of b is when x try to converge to c is L and is the same of the limit of a when x tends to be c, then the limit of f of x is also L. Okay, and that is because it is coming together and together the both function that at some point both converged in the same point, and basically the function that are in between, if each assure that they are one is greater than the function f of x, if the other is less than that function, in that point should be the limit. So for today I have this example. Imagine we have this function. This function is an exponential function. However, we have this x here in the denominator, means that the function when x tends to be 0, this function is not defined, and we cannot apply in an easy way the other rules for limits. Of course, we can do L'Hopital and some other things, but today let's suppose that we don't know that yet. So we have this function. This is how it looks like. It is an exponential function. It is not defined in the point 1. We believe the limit is there. How can we assure that? Okay, for that we define the function a will be the absolute value of x plus 1, and we know that this number here, when x is 0, basically the limit is 1. The same thing for b. The negative of the absolute value of x plus 1, same, it will be 1 when the limit tends to be 0. So this is how it should be. Basically, this is the function f of x. We know that at least in -1 to 1, this function is greater than the exponential. After some point there, the exponential will get over, of course, because it's an exponential function and this is a linear function. But at least in this interval we can have this, that for every point of x, a of x is greater than, at least for this interval. The same thing we can do for the b of x. It is below the function, at least for this interval. Okay, so what we do next, we define whenever x is in this interval, we know that this function is less than f of x, and the other function a of x is greater than f of x. So by the Squeeze theorem, we say that the limit is 1. Okay.